And on behalf of the EHPC Workshop Committee, Torsten and I would like to welcome you all to day 2 of the event. See. As usual, the website agenda and the presentations are on the link here. And we also have a working group website. A few reminders for participation etiquettes. Firstly, a request that non-presenters, if you could please mute your microphones and turn off your webcams to limit shared network bandwidth. That will be helpful. And as always, question answers that need to be addressed during the talk, please use the Zoom chat box for that. And any offline discussions, questions, comments, proposals for collaborations, ideas, thoughts, they could be directed towards the Slack channels. You'll notice there are different Slack channels for each of the sessions. And a reminder for session leads and moderators from day 1, please review the Slack channels, and even presenters, there are more additional thoughts and comments there, just to make sure that you have them addressed. Thank you for that. And today we have a few exciting talks lined up. We start with an overview of the EHPC working group. We have a session on ARM specifically related to experiences, challenges, and lessons learned when setting up ARM-based systems in the UK, the Isambard system, Astra in the United States, and Fugaku in Japan. We also have a series of invited talks focused around machine learning, specifically the different tools and frameworks and analytics, telemetry, and models that are used within the HPC Center to drive efficiency. And with that, so I do not believe any of us need an introduction to Natalie Bates, but just for fun, let me do it anyway. So Natalie Bates, as we all know, is a co-chair and has led the energy efficient HPC working group since the time of its inception in 2010. She has been a technical and executive leader during this time. And during her term, the working group has grown up to around 800 members across 25 plus countries. Prior to leading the working group, her career spanned 20 years with Intel, and she was a senior program manager there, responsible for delivering high complex programs, making sure that innovation reaches the market, focusing on multi-component and multi-partner platforms, and negotiating strategic technical industry initiatives. So with that, Natalie, thanks again for driving all of these, and over to you.
Thank you very much. And thank you, Sid. Thank you, Torsten. Thanks for the organizing committee, and thanks especially to all the participants. I'm really glad you're here. This is a very, I think, useful and productive workshop, and really glad that, sorry, I'm going to mute somebody. Really glad that that we're able to get together. So I do have my video on. You can see me. This is me. But I am going to turn it off right now because I find that my bandwidth is better. My voice quality will be better without it. So hello, everybody. And now I'm going to go to voice only. Okay, so I'm going to talk about the EHPC working group, mostly focusing on the teams. And the primary purpose behind this talk is to encourage you to join, engage, and participate. Next slide. There I am. It looks like my little poem is cut off a little bit, but it's that's me in my home. That's my husband, Peter, in the upper right-hand corner. That's my pod, and that's me working from home, life with COVID. And that's an attempt at saying hello to my Japanese counterparts. And if somebody can figure out why, let me know. It's a bit of a riddle. Next slide. So I'm going to, after this introduction, I'm going to launch right into a video. So I asked the membership just a broad request to the 800 members to tell me, why do you participate in the EEHPC working group, and would you be willing to share that with others? And I got responses from a wide variety of people: Alexander from Russia, Yetsu from Japan, Sam from the UK, Bilal from Saudi Arabia, Thomas from Germany, Greg from South Africa, and Parks from the United States. And next slide. We're now going to play bits and pieces, a collage of those responses.
So why am I part of the EEHPC working group? Well, there's a number of reasons really. First and foremost, it's great to learn from other individuals and help where I can. But secondly, it's a case of, have you ever been on site and thought, well, I wonder why we do it this way? Why do we work to these guidelines? Why don't they do it like this? Well, this would be your chance to contribute to that and actually try and make an active difference with a group of individuals that span across the whole industry to make the future better for everyone.
Participation in the energy efficiency working group helps us not just accept tendencies, but drive trends in the high-performance computing. In the end, that enables us to deliver better technology and better systems.
And so 4 years ago, I attended the EHPC workshop at ESSI, and I really enjoyed the forum, the exchange of ideas and best practice from different angles and from the presentations that I have attended. And so as a scientist, computational scientist, it was a great place for me to where I was able to see the synergy between different groups, not only from national labs in the US, but also with the vendors, the chip manufacturer, ISV, different centers from in Europe and in Japan. And thanks to the knowledge that we share and so on, I was able even to make some recommendation and changes at cost, so that have been adopted recently with the procurement of the HPC systems and data center upgrade by following the best practice. So don't wait until you are constrained with the power and cooling. Join the EEHPC group to learn how to monitor, anticipate. Otherwise, you and your user, you will not be able to maximize your investment.
I could directly share my experiences with the other experts in the group, but also with the broader community through our joint publications. In our discussions, I quickly learned to value the different perspectives everyone brings to the table. From the data center operations across the globe, but also from the research and vendor community. For instance, while my focus is on energy measurements and their use in research, others focus more on the energy efficient operation and on cooling aspects. I believe together we can make the strongest impact on the global challenging issues around energy efficiency for data centers. But also, these discussions give valuable feedback to my own research, and if we meet at workshops and conferences, it's always nice to see familiar faces.
I want to know detail of power API and know power profile of other computer systems.
The working group is well administered thanks to the dedicated efforts of a core group of hard-working individuals. The working group produces tangible outputs. The EEHPC working group is itself comprised of several subgroups. These subgroups offer the opportunity for collaboration across a wide range of areas. Participation in the community is open, and interested observers, collaborators, and contributors are encouraged to join.
We've helped the Green 500 narrow down so it has better results and tells people more what's going on with the computers rather than just flops. It's brought a lot of people together that wouldn't be together otherwise, and it's raised the awareness for, I'd say, everybody. And everybody has got something from it. Not everybody knows everything. So once you participate in a group like this, you will learn something, even though you thought you knew everything.
Thank you. Thanks, everybody. You'll have to let me know how you liked that. I thought it was really delightful. Okay, so the EEHPC working group is global, as you can see. It's open, it's free, and it's active. As Sid said, we have about 800 members from 25 plus countries. That's comprised mostly of participants from sites. However, we do have about 30% of our members are from the vendor community and 20% are from academic institutions. The one thing about the EEHPC working group that sets it apart from a lot of other working groups is that we have a very unique blend of both the facility, people from both the facility perspective and the HPC system perspective. A lot of times these two groups tend to be fairly stovepiped, and we bring them together. It's an opportunity to talk to each other and learn from each other. I'm going to mute somebody. Okay, next slide. We do have a mission. It's energy conservation and energy efficient design in high performance computing. And that's in general, not just the facility and not just the system, it's both. And it's primarily the Venn diagram, the intersection between the two. Our vision is to, reduce expenditure at the sites and potentially in the vendor community, I suppose. Curb environmental impact, that's certainly a big motivation for me personally. We do that through disseminating lessons learned and best practices, through sharing information, peer-to-peer exchange, as well as collective action. Next. So how do we do this? We employ task forces. A task force is different from a standing committee. A task force has a life, a beginning, a middle, and an end, and a pretty clear deliverable. It's motivated by you, by anyone, just, who sees a need. And it's got to be more than one person seeing the need. It's got to be somewhat of a collective effort. A few people saying, yeah, there's a real need here for us to do something. They have a sort of a vision. It doesn't have to be a really concrete proposal, but it has to be a pretty compelling need. And like I said, there has to be more than one person. There has to be a couple of people who are interested in it. From there, we convene a team. The team gets together and says, okay, what are we doing? They identify goals. What are we trying to accomplish? And then once the goals are identified, once we have a clearer understanding of what we're trying to do, then we say, okay, so what's the end result? What's the deliverable? What's the concrete value add that we're producing? It helps us to stay focused, and it's really critical in terms of task force functioning. Our intent, again, is to be short-lived. So the idea at the end, the deliverable is handed off. It's either handed off to the community generally through publications, through website postings, or it's handed off to other organizations. ASHRAE, the Green 500, the Green Grid, OCP, Power API. Those are some of the organizations that have a longer standing institutional focus than the task forces and even than the EEHPC working group that'll maintain those deliverables. So in some cases, that's who we hand it off to. And that's the virtuous cycle of continuous improvement, which task forces help to drive forward. Next. Okay, so this is actually a list of all the teams. Some of them are pretty dormant. Others of them are very active. And some of them are still ideas. So the first column is the task force convenes. That's the idea phase. And we have two of them that we've been, they've actually been on the back burner for a while. One is a maintainability task force. And we've done some work there. We've actually identified what we think are the goals of a team. And the other one is a policies team. What sorts of scheduling policies and other kinds of policies do we have in our data centers? If we articulated those policies into an optimization tool, could we help to improve energy efficiency in a more automated way? The producing teams we have a cooling controls team, an operational data analytics team, a procurement team, electrical commissioning, power API, and liquid cooling specifications. All of those teams have been in progress for a while and have actually produced publications, but they all have ongoing deliverables. So they produced one and they've decided we want to go on and produce the next deliverable. And then we have a whole lot of teams that have produced deliverables and are in more of a holding stage. WX, power measurement, liquid cooling controls, energy and power aware job scheduling and resource management, TUE, a liquid commissioning, dashboards, grid integration, and a mailing list team. And so, I'm going to talk in more detail about some of these teams. Next slide. Cooling controls team. That team opened with a sharing of case studies, identified that we had a gap in our design process and is now working on writing a white paper, which will have the scope of HPC mechanical controls, and it's focused on an operator project requirements document, and it's being led by Krista Prater and David Grant. Next slide. The electrical commissioning team that formed, identified goals, investigated the unique aspects of HPC load, that's the power load, relative to the commissioning process. And it's in the process of developing a guide to electrical commissioning that would include baseline requirements as well as the additional requirements for the unique elements of HPC data centers. And that's primarily the dynamic large loads. So 20, 30 megawatt, millisecond load change. Next. And finally, the operational data analytics team, they recently published a global survey on ODA, emerging technology and early adopter experiences and lessons learned. And they're now working on case studies on machine learning for operations. And sorry, I haven't been introducing the leads, but that one's Michael Ott. Next slide. Okay, and the procurement considerations team, that's an ongoing team, periodic updates to a document which talks about when you're writing a procurement, what are the kinds of things that you should consider with respect to energy efficiency. We published a version in 2019, and we have another one that we're working on right now. We're looking at updating section 6, which is the use cases update, focused primarily on the software stack. And that's being led by Gert and Jason. So thank you. That's the end of my talk, and I think the end of my time. I don't want to take away from the other sessions here, but if there is a question or two, I'd be glad to answer them. All right. I did just look at the chat boxes, and I'll make sure that Charlotte's not on the line, but I'll make sure that she gets your feedback, and I really appreciate it. Okay, at this point then, I'm going to turn the floor over to Woong, who's going to lead us through. He's our moderator for our next session on ARM.
Thank you, Natalie. My name is Woong Shin from Oak Ridge National Laboratory. Welcome to the ARM Operational Experiences session. So I'll just jump in. So ARM, for those who still think ARM is from mobile phones, embedded systems, and Raspberry Pis, I think it is important to know that the ARM we're talking about is significantly different. What are those daredevil thinking when they're building supercomputers out of these things? Or are they out of their mind? Probably not. So, I mean, we hope this session will enlighten what kinds of ARM systems we're talking about and what they are capable in the context of HPC. And for people who are familiar with the new HPC ARM systems, we think this particular session will be a unique one that talks about ARM in the context of energy efficiency, operational experiences, both from what Natalie said, systems perspective and the facility scale operational perspective. So for that, today, we actually invited people, the daredevils I mentioned above, people behind the first ARM production, the first pedal scale ARM, and the first fastest ARM supercomputer. And I think as far as ARM goes, it was pretty obvious that these people are the ones that who could really talk about ARM. So I hope we have your attention here. So I'm going to jump in. Before jumping in, I want to acknowledge the session organizers who significantly helped to shape the topics of this unique session, which could have been ARMless if done alone, I think. Thank you, James Laris from Sandia National Laboratory. And thank you, Oscar Hernandez and Ross Miller from Oak Ridge National Laboratory. So without further ado, I'll introduce our first speaker, Professor Simon McIntosh-Smith. He is a full professor at the University of Bristol, UK, leading the High Performance Computing Research Group. And he is currently the PI of the Isambard supercomputer for the GW4 Alliance, which Isambard is the first production ARM V8 supercomputer in the world. Simon, welcome. You have the mic.
Hello, thank you very much. Thank you for the introduction. So we'll go straight on to the next slide, and I'll start to give everyone a feel for what Isambard is all about. Obviously we're based in the UK, and it's a £4.1 million project funded by the main UK Science Research Council, EPSRC. The GW4 Alliance, it's 4 universities in the southwest of the UK, so Bristol, where I'm based, but also Bath, Exeter and Cardiff. And we teamed up with the Met Office, and it's because we wanted to look into could we use ARM-based supercomputers as a real production system and not just as a prototype. And when we first started looking at this back in 2016, things were very much still in the prototype stage. There wasn't anyone using these as real production systems. So this was not a given that this was definitely going to work. It was a bit of an exotic thing to try. So we teamed up with Cray and ARM to help make this happen. And more recently, with the developments with Fujitsu and the A64FX, we've also added Fujitsu into our collaboration. So we're actually following on with Isambard 2, following on from Isambard 1, which was a £3 million system. So we're already about £7.1 million into trying this as a long-running experiment, see how well it works. So if we go on to the next slide, please. We've just done this upgrade to Isambard 2, just happened in September, so very recently, where the system's been working so well and it's been so popular, it's been full all of the time, which is usually a good sign that things are working well. So we've just doubled the size of the production system. So it's an XE50 Cray system with Aries interconnect using Marvell ThunderX2 32-core CPUs, 2 of those in a node. So just over 21,000 cores in total. And the great thing is the system is basically full. Most in the very early days, people were coming to try the system because it was ARM, and then later on, people just started using it as any other supercomputer, which was kind of the goal. So we were very pleased when it switched to people just registering for accounts and applying for time on the system just to get science done, rather than kicking the tires because it's ARM. So that's kind of the experiment's kind of been successful when we get to that stage, because we're very interested in being able to evaluate ARM in a scientific way and see how well it performs compared to the competition. We built Isambard to include a little bit of everything else as well, all within the same system. And that means we can use a consistent software stack as much as possible across all of these different devices. And then we're really just comparing the differences in the architectures while keeping the software the same as much as we can. So we now have things like some AMD Rome nodes, some Cascade Lakes nodes. We have older Intel x86 CPUs in the system as well. Even got some IBM Power 9, as well as 2 different generations of NVIDIA GPU. And we're hoping to add some AMD GPUs and possibly some Intel GPUs soon too. So that in Isambard, all in one place, you'll be able to compare ARM with everything else out there that might interest you and do a really nice, rigorous head-to-head comparison. On to the next slide. So we've just added some exciting A64FX CPUs. If you don't know, that's the CPU that's powering Fugaku, which is the new #1 on the top 500. These are really interesting because they've got high bandwidth memory and really wide vectors, all again using the ARM architecture. Now, I've not really said anything about energy efficiency yet, which you might find surprising given the venue and given we're talking about ARM. For Isambard 1, it might surprise you to hear we weren't really interested in energy efficiency. We were more interested in, does the ARM architecture work at all as a production system? And energy efficiency was kind of a second order concern. The great thing about A64FX is, and it kind of shows some of the benefit of the ARM ecosystem, it's Fujitsu have decided to implement this and make it really, really focus on energy efficiency or performance per watt, get high performance, but with great energy efficiency, but with the same architecture. So we're able to take the same codes and run them either on our production system, our TX2 XC50, or on this A64FX system, and get the real top end of the performance per watt in a CPU. So that's very, very exciting for us. It's an Apollo 80, so it actually comes with a Cray software stack. So we get the Cray compiler for this, as well as the ARM compiler and GNU. And we're really hoping that we'll be able to get the Fujitsu compiler on here too. So we'll have all 4 of the main compilers for ARM for A64FX. And in fact, this was just used to great effect at Supercomputing a couple of weeks ago, where ARM ran their SV hackathon on it and had access to the Isambard hardware. So they had real hands-on hardware tutorial for the first time, which is great. So next slide, please. Just in case you couldn't see the artwork from the 2 different systems, we sort of put on there, so you can see how pretty they look. And that's Isambard Kingdom Brunel, who's a very famous Victorian British engineer, and that's who the systems are named after. Next slide. In terms of the actual experience with the system, originally we thought if we had 100 people want to use Isambard, we'd be really pleased. And the interest had just kept going up and up and up. We're up to about 450 users now, which in the UK for a tier 2 system, which is a regional system, that's really good. That's quite a lot of users. And the interest has stayed fairly constant. You have lots more people every month registering for accounts. And the next slide shows how busy the system's been. And really, we've been running at over 90% full and nearly 100% availability. We've only had downtimes for major upgrades. There was one interesting nationwide security incident in May this year when we took the system down for a few days just to check we hadn't been affected. Luckily, we hadn't. And then just 2 months ago, we've upgraded double the size of the production system. So we've got loads more performance. But we're now providing something like 14 million core hours a month, all on ARM, to people doing all sorts of different science, chemistry, engineering, you name it. There's people doing it on Isambard. So next slide, please. Just to show you some performance results, we've done lots of things running codes like GROMACS, which is a big molecular dynamics code, very popular in Europe. And we've shown in some work, this is actually from CUG last year, 2019, that we get really good performance. And GROMACS is a compute-bound code, which was a bit slow on ThunderX2 compared to Skylake, but actually at scale, we caught up and we're actually doing very well. So GROMACS ran well. And on the next slide, we were showing actually for an engineering code, OpenFOAM, which is a big CFD, widely used CFD code, we're also getting great results. And we generated results like this in the code paper last year, looking at all sorts of different codes. And Isambard was performing really well, even compared to what was the top end x86 systems available at the time. So we were very pleased with how it's all been working out. And next slide. For the A64FX, these are all results which we've normalized to the best for each case. We've compared A64FX with the ThunderX2s in Isambard, and then with a dual socket 56 core Skylake top end system, and then a Cascade Lake and dual socket 20 core, so 40 cores in total system. And A64FX, even though we still haven't fully deployed this system, the results are looking really good. For T-Leaf, Cloverleaf, and OpenFOAM, those are memory bandwidth bound codes. A64FX, remember this is one socket of A64FX versus 2 sockets of everything else. A64FX already has a very healthy advantage, which you would expect from its high bandwidth memory, but it's good to see that's already happening. And then BUDE is a molecular docking code used in Bristol. That's the only one so far where at the moment it's not performing quite at the level we'd expect. On A64FX, we'd expect performance that's right up there, similar to the dual socket Skylake system. But at the moment, it's about 2x slower than we would expect. So we're currently digging into what's going on there with the compilers, but it's still very early days. So early results are looking very good for A64FX. And next slide. So that's pretty much everything. Many of these results have appeared in some papers we published about Isambard. The main ones have appeared in CUG for the last couple of years. And last year, we were lucky enough to win the best paper for our Isambard paper at CUG in Montreal. Feels like a long time ago now. And you can also find lots of our results and publications that go with those, either on our group's webpage, or you can go to the Isambard webpage and have a look as well. We're very open with Isambard access. If anyone would like a little bit of time to try some scaling or any of the kinds of experiments, if you go to the Isambard webpage, you can sign up and we can give people accounts to try it there. And that's everything from me. Thank you.
Thank you, Simon. Awesome presentation. Thank you. It's exciting to see people are getting science done and interesting to see how ARMs are capable of. Thank you very much. We'll move on. Our next speaker is Kevin Pedretti from Sandia National Laboratory. He is a principal member of technical staff at Sandia, who helped designing and deploying the Astra supercomputer for NNSA DOE, United States, which is actually the first petascale ARM supercomputer, another first. Kevin, you have the mic.
Thanks, Warren. So yeah, I'm Kevin Pedretti. Happy to be here today and share a little bit of experience of what it's like to operate a ARM supercomputer for the past couple of years. So next slide, please. So what is Astra? It's about a 2,600 node compute node system made up of the HPE Apollo 70 compute node products, which I think are the first production ARM server part from HPE, certainly the first 64-bit variant. About 145,000 cores total, 2.3 petaflop peak. And it's made up of the Marvell ThunderX2 processors, much like the system Simon just discussed at Isambard. I see a question popped up already. Okay, that's for someone else. Close that. And let's see, in about a 1.2 megawatt peak. Okay, so the ThunderX2 processors we chose were the 28 core variant running at 2 gigahertz. That's not the top end part, but we thought it was a nice balance between cost, performance, and power usage. So it provided a nice balance for our workloads. And then I'll skip going through the rest of the details, but just note that we architected the system. Well, if you could go back, thanks. We architected the system to have enough memory capacity, enough storage capacity, and bandwidth to run real workloads running at scale. And that's really the reason that we did it. We wanted to, like Simon said, see if ARM even worked and prove it out for our particular workloads. This first generation system from a power efficiency or energy efficiency standpoint doesn't look that great, but ARM has a ton of potential to customize the implementation to workloads. So we've got some more details in our SC paper this year about Astra. Next slide, please. This is a picture of the system itself with a subset of the team standing in front of it. It's 36 cabinets of 72 compute nodes each, arranged in 2 rows. You can see the bus bar on the top, 40-volt bus bar that brings power into the racks. And then water cooling comes in from the floor. There's 1 cooling cabinet per 3 compute racks, which are the racks that you see that have little screens on them. I guess I don't have a pointer, but and then there's a closed air loop ducting system that flows air front to back to the compute racks. Let's see what else. So the water comes in from the floor, 208 volt comes in through the floor for the utility racks and the director class switches. And then, there's of course LED lights that are lighting up the front of the system. That's, the beautiful New Mexico night sky. Okay, next slide, please. Okay, this slide just showing that we've been doing ARM testbeds at Sandia since 2014 with a number of small scale testbed systems. Those are great for getting some experience, but a lot of the operational issues and issues that crop up don't happen until we get to a large scale system. So Astra's kind of been really critical for surfacing a lot of those things. Next slide, please. And getting to that point, what's it like to operate an ARM supercomputer? There's a number of folks in the ARM community that like to say their goal is to make ARM servers as boring as possible, meaning have them operate just like every other server that's out there, as kind of a drop-in replacement and no major surprises. And ideally, they can be combined into large-scale HPC systems to the same effect. They just operate like other systems. But there's a pretty important asterisk, right? With any new technology, it requires maturation. And right now, everything, certainly for Astra, everything was just a little bit more raw than it would be otherwise, right, for an existing technology. It'd be one thing if it was a 6th generation product and we were just kind of turning the crank and incrementally rolling something out. But with something new, there are a lot of things that come up, and that's just part of the game to work through those and mature the system and help future systems work better. So that's what I mean by boring there. It looks like a normal system from the facility level, from the IT system level. Astra actually has a narrower swing from idle power to maximum power than some other systems. At idle, it's about 700 kilowatts, and under load, running like HPL or even a memory bandwidth bound code, I guess, like HBCG. On this particular platform, they both use 1.2, 1.25 megawatts. So there's factor 2 swing. Future systems, we'd like to see that be a bigger swing, perhaps have a 10x target idle to underload. Let's see. IT system, standard racks, standard PDU per rack, the Apollo 70 chassis. And one thing, I guess, one kind of observation that came out of the experience of deploying Astra is it would be potentially useful to have two-way communication between the facility level monitoring and the IT system monitoring. And that communication is really critical for identifying issues. And right now they kind of operate in silos. So, looking at ways that we can do that, it also has potentially a lot of opportunity to take advantage of, like, we've got a thermal siphon in the building that provides free cooling, and we could shift load such that we could take better advantage of that. So I think, coming out of this, there's a lot of potential for linking these two kind of information sources up. Next slide, please. Along those same lines, when Astra was originally deployed, we didn't really have a good understanding of it, the thermal characteristics of the ARM servers, how it operated. And so when we first stood it up, we did have issues, and we didn't have a good system monitoring framework in place, right? So we went through various stages of kind of piecemeal looking at servers and looking what their environmentals were, to trying to aggregate things and look at text files, to building spreadsheets and so on that we would identify overheating nodes. But it didn't really all start to click until we put together a system monitoring framework that stored the information and let us aggregate it, and importantly, make ad hoc visualizations to investigate issues. So shown here are two plots of the same workload, a mini AMR running over several hours on 2048 nodes. So the one on the left is kind of a histogram of the power usage over time. I use power usage a lot as a proxy for how well the system's being used. But you can see there's a number of nodes. There's quite a big spread, and there's a number of nodes that are operating close to the 450 watt kind of peak cooling capacity of the system per node. Same data on the right showing, you can clearly see each dot is a different node, plotting the maximum power and maximum temperature over that whole time range. And you can clearly see there's a number of nodes that were overheating. So by being able to do kind of these ad hoc analyses, we were able to quickly identify these issues and resolve the many thermal issues. So the takeaway is, have some system monitoring and try and do it from the start. Yeah, next slide, please. Same sort of thing, the asterisk firmware immaturity. With new technologies, you should expect there to be many rounds of firmware updates. That was certainly true for Astra. One example was working with Marvell to do an update that improved the memory bandwidth from about 220 gigabytes a second a node to roughly 250 gigabytes a second per node, which was the target. And there were a number of other firmware issues as well that we had to fix, controlling fan speeds, turbo algorithms, RAS reporting issues that we had. There were a number of things. And I don't know that this is ARM specific, but as firmware gets more complicated, there's a more complicated supply chain, lots of people who have to sign the firmwares to have them trusted. It can take several weeks to months to deploy these things. So kind of the thought here is, if you're doing a first of a kind, kind of lower volume, new technology system, expect there to be lots of firmware updates, and both vendors and sites do whatever you can to try to reduce that iteration latency. Next slide, please. And then power management. So, the ARM servers, in Astra, follow the ARM server specifications. They have standard ACPI and CPPC control, things like that. And so, power control can work with shrink-wrapped operating systems, but it isn't quite as easy as that going in. We didn't really understand how power management worked on ARM. So there was a learning curve there. And also, when we first turned on the system, we sort of configured it for maximum performance and quickly hit into, instability issues, bugs in the power management and the drivers, and then just overheating issues in general. So we quickly disabled them, and the system is basically operated with power management disabled, running at a fixed 2 gigahertz clock frequency for the last couple of years, really. But recently we've been working with Marvell and HPE to try to change that and re-enable these capabilities. We've been doing a number of experiments. We've rolled out firmware updates, I guess, to enable it, and then are doing experiments to characterize the performance versus power versus temperature trade-offs. And hopefully we can enable these on the platform and be able to get higher performance while still staying within our thermal constraints. Okay.
We have to wrap up. Tech.
Yeah, thank you. I meant to set a timer and I didn't, so sorry about that. This is the last slide. Basically, is ARM the key to an energy efficient data center? Well, it's a definite maybe. ARM's an excellent ISA, but it's just an ISA, and a small amount of the power budget actually goes to decoding that. But what matter a lot more are the implementation, the architecture, and that's where ARM has a ton of potential. The ecosystem is the value of ARM, ability to specialize. And I think the future is bright there. Down at the bottom, showing Astra compared to Fugaku. So Astra's more of a kind of commodity, general purpose server grade processor, but systems like Fugaku are really showing what's possible when you take ARM, customize it for your particular workload, and the evidence is there. #1 on the top 500 Green 500. So I'll conclude there. So thanks a lot.
Thank you, Kevin. That was an awesome presentation. Boring as possible, rapid replacement. That's what's pretty interesting. Okay. Move on to the last speaker. Last speaker is Dr. Fumiyoshi Shoji from RIKEN Japan. He is the Division Director at Operations and Computer Technology Division at RIKEN Center for Computational Sciences, RCCS. He is responsible for operation and enhancement of the HPC systems and facilities for RIKEN systems such as Fugaku, the first world fastest supercomputer, which is also based on ARM. Fumiyoshi, you have the mic.
Thanks, Soon. Thank you for kind introduction. So first of all, I'd like to thank organizer for giving us this opportunity to introduce our recent activities. So in this presentation, I will briefly introduce supercomputer Fugaku and its functions for energy efficiency. And I also report evaluation result of the functions and discuss how can we use them for energy efficient operation. Next slide, please. And RIKEN Center for Computational Science has established on 2018, and former name what RIKEN AICS. And our mission includes first, operation and enhancement of the key computer and currently Fugaku. And second one is to construct a center of excellence in this research area in Japan. And last one is to develop so next generation supercomputer. And supercomputer Fugaku is a successor of the key computer, and it is ranked first place of top 500 released HPCZ Graph 500 HPC HPLAI in June and November this year, and we also have started early access program on Fugaku since April this year, and it includes attack COVID-19 projects, and there are so many remarkable outcomes, and you can see them in this URL. Next slide, please. So this table shows their comparison key computer with Fugaku. So key feature is the CPU architecture. So in key computer, we adopted Spark-based ISA, and on the other hand, for Fugaku, we use the A64FX. It's based on the ARM version 8.2a scalable vector extensions. And you can also see double precision peak performance, number of nodes, and voltage and power consumption in HPL on full node. It's actually more than two times of the K computer, and the water cooling ratio of the Fugaku is relatively increased up to 90%. Next slide, please. So I will talk about the energy saving functions of Fugaku. So this slide shows you can see the wow. So A64FX has the 5 power nodes for power optimizations. So next slide, please. And so this table shows the functions and options. For example, number of active floating point units, we can choose 1 or 2 of 2 units. And we can also choose number of active integer units, memory bandwidth, decode and issues rate, frequency control, and retention. And retention means low power mode for unused core and or node. Next slide, please. So I will show you some evaluation results. So these works have been done by Dr. Kodama and his collaborator, and was reported in EEHPC SOP workshop this year. And they evaluated all of the functions quantitatively. So I show you some results. So this slide shows the evaluation of core retention and number of FPU for the stream benchmarks. And so I'm sorry, I don't mention in details. So next slide, please. So this slide shows the evaluation core retention and the frequency control for the DGEM kernel. And so they observed all functions works well, and it is helpful for energy efficient operations. Next slide, please. So we also evaluated system level evaluation for node retention. So for the node retention case, total power consumption in idle state will be 17.7 megawatts. Okay, so and if we apply retention for compute and IO node, the power consumption can be reduced up to 50%. Okay, next slide, please. And so these functions can be used in job execution phases as follows. First, for unused node, node retention function can be applied by administrator. before job executions, power node controlled by administrator and or users. And during job executions, power node controlled by users. And after job executions, administrator return to the default settings. And again, for unused nodes, administrator apply node retention. Okay, here we have we have two discussion points. So one is the what is the suitable default settings in Pro? I mean, if we choose a number of FPU is 1, so then it will give large power saving, but users will complain like that. And second one is how far should we permit user to control power knob in job running phase, because it may give a large power saving. Next slide, please. And so, as I said, one of the most serious operational issue is power swing. So power swing in the worst case, when the retention is enabled, a power gap between idle and peak. So actually, HPC-Z is a most power consuming application on Fugaku software. And in the case, power gap will be 26 megawatts. On the other hand, if we apply, if we retention is disabled, power gap will be 17.2 megawatts. And here is our operation plan in large scale job mode. So in this mode, only one job can use full system. So in this mode, node retention function should be disabled to reduce the power gap. And we think job preview process, actually we check small scale test results and we decide and user to run the job or not. So it's very important to prevent unexpected power swing. And on the other hand, normal job scale mode, in this mode, there are so many jobs which share the system. In this mode, node retention should be enabled to reduce the energy consumption. But the maximum number of nodes per job should be limited so as not to exceed the cooling capability. So actually, our cooling facility can follow up to 15.74 megawatts in 4 minutes, or up to 17.2 megawatts in 12 minutes. So this is a hard limit, and so we have to manage job execution within this limit. Next slide, please. So we also discuss how to increase user awareness for energy efficiency. One idea is to allocate node hour and energy. So first step, increasing users' awareness for energy efficiency by informing consumed energy. And second step, if allocated energy is exhausted, the job priority is the scheduling is lower. So, but it is very difficult to keep fairness among projects because power consumption profile depends on the application program. So we have to try to develop convincing energy allocation rules based on job profile data analysis. And we also suggest recommend power knob setting from the job scaling, job profile data analysis. For example, there is memory band intensive application. We will recommend to user number of FPU should be 1, like that. Okay, next slide, please. So this is summary and the end of my talk. Thank you very much.
Thank you, Fumiyoshi, for sharing the results. I think it's pretty interesting that it has very elaborate power knob control with Gaku. Okay. So I think we have about 10 minutes. Time check. I think we are going to finish like 5. So I'll first try to address the questions to the session, the panel. The first question was on Simon, for Simon. I think he mentioned it, but just expanding a little bit, I think we can expand this question towards this. Surprisingly, I think this was, it was mentioned during the talks from Simon and Kevin. ARM is surprisingly not energy efficient. And I think that was an interesting point. So forwarding the questions, expanding from that, I would like to invite the panel to give us a little bit of comments on that. Simon, can you start?
Yeah, sure. I don't think I'd say ARM is not energy efficient. I think I'd say there's no magic, and ultimately it's not the instruction set that determines whether something is going to be energy efficient or not. So ARM in theory is no more or no less energy efficient than any other design, at least for these high-end CPUs, right? When you're in the mobile space, the amount of energy going into instruction fetch and decode might make more difference, but for large CPUs, the kind of which we all use for high performance computing, it's going to be very much a second order concern. And instead, I think that the benefit of ARM from an energy efficiency point of view is it lets an ecosystem of vendors who want to design processors pick where on the spectrum of the design space they'd like to go. And we've seen Fujitsu now decide they were going to design a very energy efficient processor, and they could use ARM as the instruction set to do that and leverage the existing ecosystem that was already targeting them. So it's not that ARM is itself more energy efficient than others, it's just it enables you to design energy efficient processors. That's our experience anyway.
I see. Thank you. Kevin, do you have any comments on that one?
No, I mean, I think that was really well put, right? It's about architecture and implementation. And, you know, it's the key question always, right, is how well does a system or a processor work for your application, right? And ARM gives you the IP ecosystem that you can tune the implementation, make a processor that works well for HPC or a specific subset of HPC. So that's where the value is in my mind.
I see. Umeyoshi?
Yeah, sorry, I'm not a specialist of the microarchitecture, but I think at least A64FX is so energy efficient function of the A60FX is very simple, I think. So as I show you the so frequency state is only 3, and the important point is there are no unexpected frequency change. It means so there are no unexpected performance degradations. So it is very important in the operation, I think. So that's all.
I see. Thank you. Interesting points. I'll move on to the questions and come back to the topic again. So there was a question from Valley Sorrell this is for Kevin. You state that there is the 780 GPM at 22C inlet. And he was wondering whether there was a performance at higher temperature documented, like at 35 or 40C. So I think this really touches the interaction between what the facility provides and how the system behaves. Kevin?
Yeah, so I turned my video on, just hi everyone. Yeah, sure, so that's a good question. So I'm coming at this sort of from, I guess, a system operator standpoint, right? I sort of have a research background. So Astra's been really fascinating to get a better handle on how the facility surrounding the HPC system works. And I'm by no means an expert, but the water temperature has been interesting. So we've moved the water temperature around and measured the impact, but we haven't formally documented or published anything about that. And certainly there's not enough thermal headroom in the system to operate with water temperatures at 35 or 40 C, just based on experience and knowing how things operate. And part of the reason for that, right, is it's an air-cooled system. So, I mean, it's water-cooled in the form of the heat exchanger cooling cabinets that we have, but there's actually air flowing through the system. So if we had close coupled water cooling to the nodes themselves, we could operate at much higher water temperature. But the way it's configured now, we might have a few degrees C of wiggle room on inlet temperature, maybe slightly more than that. But for the most part, we have to say no to that. So that's what I can say.
Okay. There's another question for. There's a question for Fumiyoshi. This is on idle power. So I'll just read it. Idle power does not depend on performance states when leveraging C states. So the behavior of idle system is very surprising to Thomas. Do you know what is an intentional architecture design to limit the power swings? Are those different kinds of power knobs well documented, or is this something you learned during operation? Fumiyoshi?
Yes, wait a moment. Sorry, I'm reading. Sorry. So sorry, I'm not sure about the so Thomas is discuss about the international architecture design.
So maybe if you don't mind, I can reiterate a little bit the question.
Thank you, Thomas. Yes, appreciate it.
So from my experience with x86 classical Intel and AMD systems, you don't have to do anything other than enabling C states to optimize idle power. So the system will, if it's functioning correctly, will always use the lowest possible power consumption in idle. Whereas your experience showed that you have to tweak manually the power knobs to reduce the idle power consumption. So this is surprising to me from an x86 perspective. So the question is, do you know if this is intentional design that the system kind of doesn't support automatic lowest power in idle? And also, like when you do these optimization with the power knobs, whether this is something that you have learned through your operation, or that is something that's like documented and you just have to look it up.
Sorry, I'm not sure about the mechanism for the Intel-based CPU, but as I said, it's very important feature that the A64FX don't have the automatically changing of the frequency and voltage. So it means, so in Intel-based CPU case, we often faced unexpected performance degradations. Okay, so at least in A64FX case, we don't have no such performance degradations. Is this an answer for you?
Well, I mean, we could go in more details, but I think this covers it. Thank you.
And I'll just jump in quick, if I can say, on Astra, right? The idle power draw does in fact depend on like what CPU frequency you have it set on, right? There's not the equivalent kind of C state, at least that we found, not the equivalent of kind of the C state sleep system. I think there's a lot of growth area, I guess, for power management and ARM systems, and we'd like to get that idle power draw down, obviously as low as possible. Ideally the systems are 100% used all the time, but in reality, that there's periods where they're idle. So
yeah, we've actually seen similar things on a single Thunder X2 node, but we just thought our mainboard was not supporting the power states correctly, because I mean, also on your system, it's like 270 watts in idle, and that's extremely high compared to the same generation of x86 processors.
Yeah, for sure. Yeah, agreed. Yeah, and changing the P state, I guess, the CPU frequency, we can take that idle power down to 136 watts. But you know that requires reconfiguring the BIOS on the system and an active move to a lower P state. So, yeah.
Okay, thank you. So I think more control versus less control, and whether the impact is reaping out from that is quite an interesting perspective to look forward. Thank you. Unfortunately, I think we ran out of time. It's 8:05. I really appreciate the participation from the speakers and everybody. Apologies for not being able to cover all the questions. We'll forward them in Slack and invite everybody to address them in the chat. And I'll hand over the mic towards the next session moderator, Torsten Wild, System Architect at HPE. Thank you very much. Torsten, you have the mic.
Perfect, thank you, Wung. Yeah, so the session that I'm sharing, it's called Towards the Practical Use of Machine Learning in HPC Data Centers. And we have three speakers, Sergey from HPE, Haik from LSZ, and Burak from the Boston University. And to lead in, I just wanted to quickly get us all on the same page in saying, so what is actually machine learning? And if we look at machine learning, what it really means is that we apply some type of artificial intelligence that has the ability to automatically learn and improve from some type of data or experience without being actually explicitly programmed to perform some specific functions. And so machine learning really is then focusing on writing or developing computer programs that can access data and at the end use that data to learn for themselves. So the process, like I just stated, is really the critical piece of where it all starts is actually having enough valuable and correct data, because the data is really what is used to then automatically try to create some models and then use those models to really automatically do something, intervene, or do some actions according to the models that were learned. And there are two techniques which we will discuss during the presentations. So just to give you a heads up, so one is kind of supervised learning, which means that data is already classified or labeled so that the machine learning algorithm already knows kind of what the data represents. Whereas the second approach is kind of unsupervised learning, where data is unlabeled, so not classified. And usually that's also then harder for the machine learning algorithm to really develop something out of that data. And with that, I would like to give the mic to Sergey. So I will share your slides, Sergey. So wait some seconds here. Okay, there it is. It's a little bit harder if you are the session chair and the slide sharer. So, but I'm managing it. So perfect, Sergey, go ahead.
Thank you, Torsten. My name is Sergey. I'm a research engineer at Hewlett Packard Labs. I will briefly talk about our experience and lessons learned in developing and deploying machine learning models for anomaly detection for data centers at scale. So that's a joint work between HP and the National Renewable Energy Lab. So this is a brief overview of my talk. I would like to briefly talk about why do we want to use ML-based anomaly detection models at data centers. I'll talk very briefly about our journey from simple statistical models to machine learning and deep learning models. I will have one slide describing how we train these models and test them and put them into production, given large number of data points and metrics we have to deal with. And I'll conclude by sharing some of the lessons we have learned on our path. Next slide, please. Right, so I don't think that I need to really, go into details explaining why do we want to use machine learning for solving different kinds of problems, in particular for solving different problems related to HPC data centers, such as anomaly detection. The problem is that we have really a large number of different and diverse data available there, coming from both facility and IT. Those metrics are different. They have different parameters. They can be stationary, non-stationary, unimodal, multimodal, and so on and so forth. And also, it's interesting that we don't really know where to look, right? If we have even hundreds, maybe thousands of different metrics, we can just put all them on our dashboards and just look, because it's just not manageable. Anomaly detection is not the only task that can be solved with machine learning methods. We also have different a number of other different problems in mind, such as power usage effectiveness optimization, workload characterization, and some other tasks related to data centers. It's not always sufficient to just use a simple methods such as setting a threshold on a metric to be able to identify anomalous behavior, again because of the different metric characteristics that we have to deal with at data centers. And sometimes we really need to use more advanced methods, because some of the anomalous behaviors cannot be identified just looking at the metric. Things like contextual anomalies or those that cannot really be identified just by looking at the metric. So another other problem obviously is that we have, as I mentioned, we have a really large number of different metrics coming at high rates. If you go and read some of the papers on anomaly detection, sometimes they consider a particular use case, but we have to deal with a large number of metrics, so we kind of have to automate some of the steps, and this is where unsupervised machine learning methods that Thorsten mentions can really help. Next slide, please. Right, so this is a briefly basically structure of my talk. I'll talk very briefly about models we started with, univariate statistical anomaly detection models. Then I'll go to describing a little bit more advanced univariate models based on some of the neural network architectures. I'll very briefly cover multivariate anomaly detection models that we use, and I'll talk about how we automate, how we enable training and testing these models at scale on a diverse set of metrics. Right, so we started with the simple univariate anomaly detection models, also known as single metric models, that operate on individual metrics, right? So on the right-hand side, we show here a cooling rack controller with 4 metrics, and we use 4 different models, right? 1 model for each metric, starting from simple statistical approaches such as a z-score, together with the different pre-processing methods. So we compute residuals, which is a difference between a metric and its trend that is estimated real time. And assuming that these residuals are distributed according to some known distribution, we can identify what points are anomalous and what are not. So this is a very simple algorithm that's available pretty much in every tool that visualizes these metrics. Next slide, please. So we also use a bit more advanced statistical methods that compare distributions of metric values in time windows. I know with the expected one. So we discretize the time series into k buckets and then compute histogram, and then we use Kullback-Leibler divergence as a similarity measure. So here on this slide, I just briefly show an example of behavior that can be identified with these algorithms. We don't really set any thresholds or set points on this metric. Rather, we just compare distribution, statistical distribution, statistical parameters of metrics on a large enough windows so that we can identify things like those depicted at this slide. So other methods that we've been using are based on forecasting models. So starting from well-known RIMA and going to deep learning models based on such architectures as fully connected neural networks and recurrent neural networks. So similar to other models, in this particular case, large forecasting errors indicate anomalies in input data, right? So the whole point of building anomaly detection models is to build a model of the data, whether that's distribution of residuals or parameters of statistical distribution of metrics inside moving windows or forecasting models or anything else. We just consider those as models of our data, and then any input data that doesn't fit or is not consistent with that model is considered to be an anomalous data. So these forecasting models work just fine. We don't really need labels. We just need to ensure that our data sets don't contain too many anomalous data points, so that they don't impact our models, and we don't really learn anomalous behavior. Rather, we learn anomalous behavior, and then based on forecasting error, we decide whether input data is anomalous or not. So all these models work great, but sometimes we need to go and to use multivariate models. Next slide, please. Yes. So right. So we condition one metric on another if they depend in some way on each other. So for instance, water flow and pump speed. In this case, building a model that processes multiple metrics can help in detecting cases where metric values are not consistent with each other. A temperature value could be okay, but not when IT load is this much. So here, colon distribution unit for input metrics are fed into a single model that produces one anomaly score for all input metrics, right? And it can detect cases, for instance, when water flow and pressure not the ones expected for the given pump speed, for instance. So we've developed a library targeted for time series data. It pre-processes data on the fly and then applies different kinds of transformations to make training examples consistent with the model's input requirements. The most widely used neural network-based models for anomaly detection are autoencoders. One is depicted here on the right-hand side. So basically, it consists of two models, encoder and decoder. An encoder takes input and for a sequence of nonlinear transformations, projects that into usually a smaller dimensional space called the code or a latent representation, and then decoder takes the code and reconstructs the inputs. Encoders and decoders have similar architecture for architectures like recurrent neural networks and copies of each other for fully connected models. So similar to forecasting-based models, large reconstruction error here indicates an anomaly in input data. Next slide, please. So this is just a very brief example how this looks like. We have a single model that runs for input metrics, and then we use training data set. We assume that the data set doesn't contain a lot of anomalous data, mostly nominal, and then we build those models, and then we apply these models to real-time data coming in real time. Great advantage of these models is that detection delay is almost zero. So we produce results as we go, and then we can identify different anomalous behavior in the data. So just one example here on this slide. Next slide, please. Right. So we run these models real-time consuming data from platforms such as Kafka, which is the source of input data and destination for for anomaly detection results, and other artifacts such as alerts and notifications. So there are several interesting challenges associated with it. For instance, like what's the right way of storing and serving potentially thousands, tens of thousands of different models. These models can be lightweight neural networks with 30 millisecond response latency, or statistical models that provide response within just 2 milliseconds, something like that. Obviously, one anomaly detection algorithm doesn't fit all types of metrics and anomalies. I mentioned briefly, metrics can be stationary and non-stationary, taking categorical values, be binary and multimodal, and so on and so forth. So we address this challenge from two different angles. We run hyperparameter optimization experiments, trying different configurations of anomaly detection pipelines. This is kind of visualized here on the right-hand side with this loop of different models which we try. And so once
1 minute.
Yes, so once good models are found, we run supervised and unsupervised evaluation. So we take a model and a data set and then run the model against it. So in certain cases, as I demonstrated on my previous slide, I think we do have information about anomalous behavior, so it's kind of supervised evaluation. But most of our data is nominal. So we take that nominal data and inject artificially generated anomalies. And we developed a framework for that. Next slide, please. This is just a very brief example. I'm not going to be spending that much time, but here we have input metric, which is a green curve, which is a nominal in the first part of this chart. And then we start injecting artificially generated anomalies, right? So that's kind of unsupervised evaluation. Then we can take a model, take a data set, which contains mostly nominal data. Then we run this loop many, many times. And then we see what models are capable of, what they can detect, and what they can't detect. Then we store this information into our databases so that later, we can better match input metric and anomaly detection models. Next slide, please. I'm not going to be saying that much. This is basically a framework that allows us to train these models, match models with input metrics, run hyperparameter optimization experiments, which is shown here on the left-hand side. Then we take those trained models and run them through unsupervised evaluation loop. And then the models that are, verified and validated are put into production. Next slide, please. Right, lessons learned. I think both of these features are critically important, being able to use advanced machine learning models for anomaly detection and run them real time so that detection delay is close to zero, so that we have time to respond to anomalies we identify. Labels are really hard to get, so we use unsupervised models as much as we, try to use unsupervised models for training models and for evaluation. Many models that we tried out of the box, they just don't work because of the, I think, nature of this, real-time noisy data sets. Also, some interesting topics for research are how to reduce false positives, how to produce more intelligent alerts, and maybe we can take advantage of recent advances in end-to-end training, which is very popular in things like in areas like automatic speech recognition and natural language processing, where we can train single models from end to end, take input metrics, and then produce alerts right away.
Okay, sorry.
Yes, that's it. Thank you.
Perfect. Thanks, Sergey. That was very interesting. Let me switch to our next speaker. Our next speaker is Heike from LSZ. And I just managed to unshare my screen, but now it should actually work, Heike.
Yeah,
So
perfect.
please,
Thank you,
go
Torsten.
ahead.
Yeah, thank you very much, Torsten. So welcome, everybody. It is my pleasure to share with you some of our recent activities towards energy-aware management of modern data centers. And many thanks again to organizers for this opportunity. Next slide, please. So I guess this is not the audience where I should actually motivate why do we care about energy efficiency at all, but just for illustrative purposes, here you see the energy cost of Leibniz Supercomputing Center from 2000 to 2018 and 19, and certain estimates for 20 and 21. So as you can see, our electricity bill has been increasing throughout this year. It's reaching recently to 8 million per annum, which does not include any maintenance, staff, or hardware costs. This is just pure electricity costs. But the unfortunate part about this is that the annual bill can be even larger if we further consider the contractual agreements with utility providers, where basically data centers are required to stay within certain power bands, otherwise implying penalty fees. So this forces data centers to look at certain frameworks capable of forecasting the potential power consumption of the data center. And not only it is important to notify on the potential power violations, but it is also important to basically have a framework that is capable of advising on possible configurations that could mitigate forcing violations of a power threshold, for instance. And obviously, the importance of such predictive frameworks becomes even more vivid when we are considering the usage of renewable energy sources, where the dynamics of the available power for a given time period should certainly be taken into account. Next slide, please. So for that reason, LRZ has started the development of a machine learning-based framework, which is referred to as Infrastructure Data Analyzer and Forecaster, so IDAF in short. So, and this framework is not only capable of forecasting potential power consumption of your cooling infrastructure, for instance, but it is further developed to assist in solving various questions that do arise during day-to-day operations. So, and here you see basically some assembly of the examples where this framework is kind of handy. So for instance, consider a case where you have a data center with 5 cooling towers, where you can actively monitor the power profile of your cooling infrastructure, as well as the inlet water temperature that gets pumped into the system. So assume further that you have certain power cap, for instance, coming from the contractual agreements that I earlier mentioned. And you have actually a natural limit on the inlet temperature that you pump into the compute node specified by your system vendor, for instance. Assume further that at a certain time, you take 2 of your cooling towers into maintenance. And the natural questions you're gonna ask yourself would be, okay, can I actually deliver the required inlet temperature with the existing 3 cooling towers? Can I do that without violating the power cap? And if so, what would be the optimal way? And last but not least, assume further that you basically have a compute and resource hungry job in a job queue, and you have a user with whom you have certain service level agreements, and where you promise to execute his or her applications as fast as possible. And the questions you're going to ask is whether you can execute actually that application within the constraints you have. Next slide, please. So in our approach, we rely on supervised machine learning technique. And thanks, Thorsten, for explaining the supervised ML so that I don't now waste more time for that. And by utilizing supervised machine learning techniques, one of the simple challenges we had was the need to cast the time series forecasting problem to a corresponding supervised learning one. And this is usually achieved by adding lags of measurements to the input set. And as the number of lags are generally explored as a hyperparameter as well, we had a simple auxiliary method that was placed to transform given time series data of say x1, x2 to xk independent variables and target y variable to a format presented here in the lower part of this slide that is basically further used for supervised learning. And it is worth noting that similarly, the time series data can be casted to support for forecasting of more than one measurement point for in future. As you can see here, we can actually have easily modified it to have a vector of target variable in question to be forecasted. Next slide, please. So various feature extraction techniques like mutual information, univative feature selection, as well as corresponding domain knowledge were used to ensure that the reduction of input parameters was in place. So we really wanted to minimize the number of input parameters to the network so that it also eases the life of data center operators and managers who are basically foreseen target users of this framework. So here you see what I call base input parameters, which are, as you can see, number of active cooling towers, the flow rate of cooling circuits, the supply temperature to the cooling circuit, the outside air wet bulb temperature, the total number of active fans for all active cooling towers, and average fan splits of all active cooling towers. So these are the base input parameters. And in addition to those, the network also takes the previous measurements of the target variable in question, as this data comes for free anyway. Next slide, please. So here you'll see a forecasting result for system inlet temperature. for a 1.5 year unseen operational data. So the trained model is based on a special type of recurrent neural networks referred to as long short-term memory network. And the model itself is a stacked LSTM model. So we have a couple of layers of LSTM here. And in case you are wondering, for instance, about the lags, so basically the look back parameter that we use for looking back in order to conduct the forecast for future events, it was set to 3 hours here. So we look back 3 hours to conduct the events for the next 5, 10, 15, 20, 25, 30 minutes, right? And here you see, for instance, one of these forecasting results. Next slide, please. So yeah, here you see some other forecasting results for other key performance indicator, namely cooling power consumption. Again, 2 years of operational data was used to train the network, and you see the results on a 1.5 year of unseen operational data. Next slide, please. And we have, obviously, we do support other KPIs. So to conclude, I would actually like to briefly provide you a high-level overview of the interplay of different components we have been so far developing at LRZ. And if we go back to my example with resource and computational hungry job, which needs to complete as soon as possible due to certain SLAs you have with the user. And for doing so, you would like to, for instance, assign the highest CPU frequency to the job that you have in the queue, right? And for that, first thing you need to do is to evaluate whether there is enough power envelope available for the assignment of the highest CPU frequency. And the next, you would also need to understand whether you are capable of delivering the required inlet temperature to the compute node in question that allows the eventual execution at 2.7 gigahertz, for instance. And this is basically a chain of questions that is tackled with various components presented here that are developed at LRZ. And you can see where basically functionality of presented EDAP framework lies. Next slide, please. Again, due to time limitations, I'm unfortunately not able to cover all the peculiarities of the presented framework, but for more details and internals of the presented framework, please feel free to check the paper here. Next slide, please. So what do we do currently? So in parallel to further development and fine-tuning of the framework, we are also evaluating the transferability approach of the developed framework and trying to assess whether or not the other data centers could basically benefit from already trained frameworks on operational data. And I'm happy to state basically that we have recently started a collaboration with NERSC, and we are pushing these activities forward. And if you are interested, basically, please do feel free to contact me, and let's have fun with squeezing the operational data. So next slide, please. So yeah, this is basically it from my side for today. Here are my contact details. Please stay connected. Thank you. And I guess I didn't violate the time constraint, Torsten.
No, that was perfect, actually. Right on the mark. All right, thanks, Heike. The next speaker is Burak. So Burak, you have the mic.
Yes, thank you, Torsten. So morning, everyone. This is Burak. I'm a PhD student at Master University from Peak Lab Research Group and working under the supervision of Professor Ayşe Coşkun. Today, I'll briefly share our previous and ongoing research work in machine learning-based performance analytics for HPC systems. So next slide, please. So Heike and Sergi already made a great introduction. So as you know, we are able to collect terabytes of instrumentation data per day, and this could be in the form of logs, performance metrics, or traces. So in the right figure, I'm showing here 199 performance metrics out of 2000 collected during an application run. As you can see, next slide. The challenge is we can collect thousands of metrics from each computing node per second granularity, but this data is generally too large and noisy for manual analysis. That's why machine learning is kind of must nowadays. And we also know that HPC applications behaviors vary a lot. So we have like tons of challenges. So what's the solution? Next slide, please. So novel solutions increasingly use machine learning, as Sergi and like Heike also proved that to analyze HPC telemetry data. And to just give you an insight, what can we learn from this data is we can understand what type of applications are we running in those supercomputers, and we can detect performance variations. And even more than that, we can find optimal configuration for the applications. Next slide. So in here, let's look at the definition of the performance variation. Sergey introduced us into the anomaly detection world. Actually, the performance variation is a subset, and in this work, we are trying to diagnose what kind of problems occur. It's basically lower granularity compared to a high-level anomalous versus healthy. We are trying to basically say what was the main reasons behind that performance variation. And those performance variations mainly cause, variable running time. It can terminate jobs or definitely waste all of the computing power and degrade the performance that we have. And main cause of those variations are actually performance anomalies. And those might be coming from network contention, some orphan processes, and other problems that we don't know from the hardware side. Next slide, please. So in our work, what we have done was we collected performance monitoring data using LDMS from the application runs with second granularity. In terms of metrics, we have hardware counters, memory CPU usage metrics, and we can collect like thousands of time series per node. Next slide. We have then we applied some statistical feature extraction to those time series data points, and to reduce the complexity, to achieve a lower overhead actually during the runtime analysis. We also applied feature selection where we choose the important features. After that, in the next slide, we trained machine learning models. And these were like classical machine learning models such as random forest, decision tree, and SVMs. So next slide, please. And then at runtime, like we applied the same strategy actually, because in those HPC systems, we have continuous monitoring systems that we can collect data. And then we again extract their features. And at the end, we also include a false positive filter because we are analyzing that data in the frame of seconds. So this false positive filter prevents the glitches in the consecutive time window. So basically, before we are making a diagnosis or giving a classification result, we are looking, let's say we are looking and making sure that we observe that performance anomaly for 3 consecutive time windows. And in the next slide, I'll show the evaluation and some results. So in a HPC cluster located at Sandia National Labs, we diagnosed 98% of the injected performance anomalies with 0.3 false alarm rate, and random forest was the best performer across other methods that we used, also comparing with the other baselines that we have. Also, to just stress it out, false alarm rate is very, very important when you deploy a model, because you don't want to raise false alarms across the all administrator network. So that's great, but this was done on like an experimental cluster. So what is missing is actually in the next slide. So then what we have done was we deployed this anomaly diagnosis framework to Eclipse, which is a production HPC system at Sandia National Labs. And in here you are seeing an image where we have where we provide user some status, where we provide user our results for node level or job level anomaly diagnosis results, and user can investigate and see the details for the detected performance variations for specific time interval according to their job, and access to the explanations for those performance variations. So that's great. When we deploy the model, I just want to jump into another topic, but what happens is it's a very, very hype topic nowadays, actually. When we deploy a model, in the next slide, I'll show in another perspective. I know I'm going a little bit fast, but in here, I'm just trying to give you an overview of what's going on currently in this field. So like, let's say we deploy those models, but there's another perspective that arises, whether we should trust those models or not. And we, as a system administrators or users, we want to understand the model's predictions, or like more important than that, like, should we trust them? Should we take actions according to the decisions of those models? And in the next slide, I'll briefly mention about what is black box AI. So black box AI is like basically what we have been constantly mentioning. We just have an AI product here, and then we end up with the decision or just the classification result. And as an end user or system administrator, you don't understand actually why model did that, why model make the following prediction, or like how can I correct that misprediction so I can understand, how to fix the system, or how can I take the action. So in the next slide, I'm showing the explainable AI perspective where we are trying to explain the internal mechanisms of a machine learning model in terms of human terminology. And it's XAI product, we provide decision along with the explanation so user can understand the model's decision in a better way. So I just would love to briefly mention what we recently developed. It's counterfactual explanations for time series classification models. So what's happening here is, to just briefly mention what is counterfactual. It basically describes a causal situation in the form of, let's say, we are, I think, all familiar with that. If metric X was not exceeding metric Y over this time, our test sample or our sample that we are trying to understand wouldn't be classified as memory leakage. And then we designed Comte to explain time series classification models by providing most important time series to flip the prediction. So to end user, we are basically, if you look at the figure, our explanation suggests that we have page allocation counter, and you can see an oscillating behavior. And orange line shows the explanation, and this should be replaced. Like if you have like more constant page allocations instead of oscillating ones, you wouldn't have a memory leakage. It's a very intuitive example. That's why I put it. But we can make we can make a better understanding of a difficult problems by using explainability perspective. And we applied our method to some famous ML-based HPC frameworks and in data sets, and then outperformed state-of-the-art methods in several metrics. So in the next slide, it's just basically a summary. So machine learning, as we can see, is a key aspect of efficient resource utilization and to prevent, to prevent ineffective usage of the resources that we have. It's very promising. And also when we are deploying models or when we are using machine learning, there's other perspective that we shouldn't forget about is the explainability, because it's critical for deployment scenarios. And thank you. We would love to hear feedback and would love to collaborate. You can shoot me an email from baksar@bu.edu. Thanks, and we'll be happy to, I think, all of us to answer questions if there are some. Thank you.
Perfect, Burak. And thanks all the speakers, Sergey, Haik, Burak, great job. Let me stop sharing, and now we go to the Q&A part. And apologies if I have to scroll up a little bit because I can't really follow the whole thing by also sharing the slides. So let me see if I can find the top question here actually. Oh, I think that looks like the start. Okay. Randy was saying, so perhaps not computer program, but rather algorithm, and the results are inference outcomes. A model runs the data to get the outcomes. Sergey, are you using ReLU for a federated learning approach?
No, we don't use federated learning type training model type training approach. I guess because in our case we build sort of a data center model. We build models for a single data center or for a single system. So we do have access to the whole data set. We don't need to care that much right now about privacy issues associated with training models using data from different organizations and from different data centers. So that has not been our focus so far. We take a system, we build models for that system. So I guess there's no need to use federated learning, at least for now.
The next question is also for you, Sergey. It's like, so why did you start with anomaly detection? Was there any other thing you could have started with, or so why was anomaly detection chosen to start the effort with Unreal, I think?
I think it's kind of important, and we did some survey. I think you should know that that data center outages result in really, in really large costs associated with that. So being able to to detect critical behavior that may impact on data center health status is kind of important. And also, we do have other problems in mind. I think I mentioned some of those, such as power usage effectiveness and things like predictive scheduling of cooling, introducing some kind of autonomous control in the data center. That's on our plan, but I think anomaly detection was kind of obvious problem to start with. Yeah.
Thanks, Sergey. I think the next one is for Heike. So from Randy, did you compare LSTMs to RNN? I guess that's recurrent neural networks or something.
Yes, we did, but since I mentioned that there was an issue of time lagging, so LSTMs to perform better when you have to consider bigger, basically, lags of time in the past. So LSTMs do better job in comparison to RNNs, and this is also true not for time series data, but also for natural language processing. For the sake of completeness, we are also currently looking at temporal convolutional networks. So they seem to be promising alternative to LSTMs for time series data. So we are looking into that as well. Thank you.
Thanks, Heike. The next one is for Burak. So how do you collect the data for training? So how do you know that certain behavior is a memory leak?
Yeah, that's a good question, because that's I think our main challenge in our domain. We don't have the ground truth, as you all know, because what we assume is we assume like most of the time, majority of the time, the running applications are normal, like we don't observe those variations. However, like to basically create a generic benchmark for that, we released an open source synthetic anomaly injection suite, HPAS. I think just posted the link as well. So what we are trying to do is we are running applications with injected anomalies, and this is how we are labeling. So that is the previous approach that we've been doing. And like, I know it's basically raises a ground truth issues, but I think that is how can we approach the problem if we want to diagnose or understand the root causes behind that.
Perfect. Thanks, Burak. So I think that's all the questions I can see in the chat. And we are also, I think, right on time, Sid, for you to do the closing. And a reminder again, so on the Slack channel, you can still ask questions, and hopefully the presenters can still answer you there as well. So thanks, everybody, and thanks, Burak, Heike, and Sergey for the interesting presentation. And with that, off to you, Sid.
Thank you, Torsten. Well, Natalie, if you would like to chime in, or I could close as well.
Yeah, I would like to chime in. Thank you, Sid. And please help me if there's other things that I miss. So first of all, I would like to say that there's a lot of work that goes into the EE-HPC working group. There's the teams, the leadership, the workshop, the speakers, even you, the participants. There's a lot of effort here. It's an extraordinary group of people. It's an extraordinary, I think, community. And I think I really want to express my gratitude to all of you for your contributions. I think we're making a difference. I think we have more difference we can make moving forward. And so I really want to thank you and encourage you to continue, and looking forward to working with all of you whom I already know, as well as new people. There are Slack channels, and I have taken all of the chat and put it on the Slack channels. So I would like to encourage all of us to become slackers, as Randy says. People that are familiar with Slack. I think it's a capability that could be very useful. It allows us to have hallway discussions, both, before, during, after these workshops, maybe even continue it on in the future. Right now, a lot of our discussions tend to be email based. And that can be either cumbersome because our email boxes get really full, or exclusive. The Slack channel allows for more participation and theoretically allows for more participation and coming in and out. And I think it could be, however, a really good way to have technical discussions on an ongoing basis for some of these topics. So I'd really encourage all of you. I know that there's an overhead to learning Slack, to getting it set up, to figuring out how to use it, but I really encourage all of you to try and go there and let's see it. Let's give it a try. Let's see if we can work. Let's see if it's an effective tool for us. We also we have the EEHPC Working Group website, and that's a great place for static information, for sharing information that is, deliver the publications, the deliverables that we've already attained. We actually also, though, have these Google Sites that we're using for workshops. And so this workshop has all of the information posted that we've already presented. It has the Slack channels. It has videos that were teasers, trying to get people to participate. It is going to have a recording of the workshop posted on it as well. So Sid, if you could also just for me post the link to the EEHPC Working Group join page. Great, that's the general website, and there's a join page on there for anybody who isn't already a member and wants to join. We would normally be announcing our workshops for next year at this workshop. However, things are still uncertain. I can tell you that our thoughts are to host a workshop at SC21 in St. Louis. So that is what we're thinking. We are seriously considering making that workshop look more like the EEHPC SOP workshop and less of an invitational talk workshop. So having it a paper workshop, but that decision has not been fully made. We are also looking at creating another workshop, which would be held like this one, which would be held on, in the area of one of the major DOE sites. And specifically, we're looking at Albuquerque and Sandia National Lab. But that's pretty dependent on COVID and travel restrictions. And so we're not certain about whether or not we were going to do that. We were thinking of doing that in the late summer timeframe. But again, that's uncertain. Are there any questions that anybody has for me about the EEHPC working group?
Comment maybe that people should reach out to you if they'd like to contribute to any of the teams that you presented.
Oh, yes. Or if they have any ideas for creating new teams. And thank you, Sid. Okay. Well, with that, then I think we are probably done. We've already had our beer party and our happy hour. So right now we can just go out and enjoy the whatever kind of weather you're enjoying.
Thank you, Natalie.
Thanks.
Yeah, thanks,
Thanks.
Natalie. Very good. Thanks, Sid.
All right.
Thanks, everybody.
For joining.
Thank you, everybody.
Thank you.
Thanks. Bye-bye.
Bye.
Thank you. Bye-bye.